am deeply honored to have been chosen to deliver the fourth Sir Alan Muir Wood Lecture. This lecture is presented in honor of the life of Sir Alan Muir Wood and his contribution to underground construction. Alan Muir Wood was one of the world's leading civil engineers. He was a founder of the ITA in 1974, as we heard, and he was the first president and the lifetime honorary president of the ITA. I had the pleasure of meeting Sir Alan on several occasions, first in London, and then a couple of years later in South Africa, and more recently in Italy. Sir Alan was always interested in the development of progress in the technology of machine tunneling. We discussed the state of progress and the barriers to the use of tunneling machines, especially in our discussions in South Africa with the Orange Fish scheme. Alan was always friendly, inquisitive, and encouraging to me. He was known to be conservative in his engineering views, but was open to consider innovative approaches to underground construction. We all have been blessed by his leadership. His accomplishments have made a lasting impression on the tunneling industry. So, to continue, Mr. President, former ITA presidents, the Madam Minister, I guess she's no longer here, delegates, ladies and gentlemen, my lecture will be mostly about machine tunneling with the historic perspective and how things have been changing and developing. I will start at the beginning with the idea of using a machine to bore a tunnel. It started in 1967, years ago at Mont-Cenis, not far from here. I will show a series of historic slides about these early tunneling machines, and my lecture will concentrate on pictures mostly from the Robbins Company. I hope I'm able to convey that there are many very capable competitors in our business. I just have more Robbins slides than any of the others. In 1846, a Belgian mining engineer, Henri Maus, conceived of the idea of building a tunneling machine to bore a rail tunnel in hard alpine rock to make an improved connection between Italy and France. His concept was a percussive drill employing 80 drill bits, each of which was operated with a spring-loaded striker. This was before we had compressed air, before we had even dynamite, but it was a job that finally came to the use of black powder, because this machine, although it was heavily tested, it really didn't make the grade. Another machine was designed and built only 5 years after Maus, in 1851, by Charles Wilson in Boston, Massachusetts. This machine was to bore the Hoosac Mountain Railroad Tunnel. It eventually bored only 3 meters in very tough metamorphic rock before being abandoned. But it employed some very ingenious features. A rotary cutter head, in this case with double rotary axes, disc cutters. Rolling cutters were even then recognized as being essential to boring hard rock. So to acknowledge Barbara Stack. We would have no knowledge of this fascinating history of tunneling machines if it were not for Barbara Stack. She is an Australian researcher, a historian, a chronicler, and a marvelous writer. We owe this huge field of knowledge to Barbara Stack. we've used some of her information to put a little timeline and throw a few more ancient slides in addition to those of Mouse and Wilson. We now come to Cook and Hunter, 1865, Brunton in 1869. Satellite disc cutters, by the way. A Spaniard named Unanue in 1903 with 17 percussive hammers run by steam. Leah Nelson in 1907, 26 gear-type rotating cutters, cutting about 90% of the area of the face, but leaving a large central core to be removed independently. Whitaker, a machine tested on the Channel Tunnel site in the Shakespeare Cliff in 1922. And so that's just a few of the ancient tunneling machines. Barbara Stack identified 45 different types of rock tunneling machines between 1846 and 1952. Tunneling machine development seems to have come in bunches, with gaps of 10 to 30 years. Many of these inventors must have believed they were the first person to conceive the idea of a tunneling machine. That was certainly the case of my father, James Robbins. My father, Jim Robbins, was a mining engineer and an inventor. He moved his family from Alaska, where he was mining gold, to Chicago, Illinois, when the mine was forced to close due to the Second World War. In that area, he started consulting with Illinois coal mining companies, and he discovered an old mining machine, and that hadn't been used for many years. Jim Robbins was funded by the CW&F Coal Company to rebuild this machine and try to make it work, which he did. That's the first machine that he built, or rebuilt. And the next slide is the view of the coal face, which shows the cutter heads and a trimming chain bar to make the top and bottom flat. So you can see the pattern of the cutters. Jim Robbins built 4 coal miners between 1947 and 51. He sold this development and his 14 patents to the Goodman Company of Chicago, a manufacturer of electric mining machinery. Now we're into 1950. Here we can see the Fort Randall Dam on the Missouri River. This tunneling system was unique in that is possibly due to the fact that there was a weak shale rock in the tunnels that had to be built at Fort Randall. The Goodman coal saw was used to cut the periphery of the tunnel, and the central block of rock was blasted. The Oahe Dam, a bit further downstream on the Missouri River, was to be the next major project. Here we can see the first tunneling machine for the Oahe Dam. Jim Robbins convinced the contractor, F.K. Mitry, to allow him to design and finance the construction of a machine that would bore the entire face and eliminate blasting and loading. So this machine was the first of the new age of rock boring tunneling machines to start a new era that has lasted to this time and on into the future. This machine broke an existing world tunneling record of 18.5 meters in an 8-hour shift. The machine was an economic success for Mitry, who made a profit. This is also a novel experience for a tunneling machine. This machine and 3 others for this project were completed. They all completed their work, and the machine tunneling this was a first. Between 1955 and 57, several smaller hard rock machines were built to bore sewer and water tunnels, and the rock proved to be too hard. In this case, dolomitic rock in Chicago and limestone and sandstone in Pittsburgh. None of these machines were a success, and all were withdrawn from their tunnels. Here we can see the Pittsburgh sewer tunnel with layered hard sediments, and the marks show clearly the drag pick grooves and traces of rolling disc cutters in between the grooves. These picks failed very quickly. Now in 1956, the Humber River sewer was built near Toronto, Ontario. And there was a very significant breakthrough here of any machine development over the last 100 years. The engineering materials were now harder, tougher, better bearings, better seals. And here you can see the way the previous tunneling cutter systems were, with the drag picks and the disc cutters rolling between them. And now I will have, I hope, a little video here. There's a little breakthrough to start with, a tunnel breakthrough, and then a laboratory test at the Colorado School of Mines in their rock laboratory. So you can see how these cutters work. They're basically just crushing the rock. Here you see a view of the cutter head designed for only disc cutters, and there you see Jim Robbins in the driver's seat of that machine. This was a very important breakthrough, and this use of disc cutters only in hard rock has survived for the next 60 years, and then, of course, sometime into the future. A year and a half later, Jim Robbins died in December 1958 when he crashed his airplane. His contribution to machine tunneling was profound. So now there's a list of some other concepts that worked. There was an interruption of almost a year when the Robbins Company put the last tunneling machine into service at Oahe Dam. Then our continued proposals paid off. We made a contract with the Hydroelectric Commission of Tasmania, and we were able to ramp up our activities. So here we see the Poatina tunneling machine from Tasmania. It was built in 1959 and 60. The owner of the HEC of Tasmania was the ideal contractor to push forward and develop more machine tunneling success. They could fix anything that needed to be fixed or modified. They just needed really good cutters and the basic machine to work, and that's what they got. Here we have also an unusual gripper mechanism, which we developed at that time. This feature allowed the cutters to last much longer because the machine could be steered continuously. Now this machine achieved a tunnel rate of 229 meters in one 6-day week. This was another world's tunneling record. With the advent of several tunneling machines achieving real success, an increased number of contractors began to see this equipment as a possible new tool to consider when bidding a rock tunnel. When several machines set world tunneling records for advance rates tunneling machines became even more appealing. This fact was also noticed by construction equipment manufacturers. So we have here a rapid explosion of designers and builders of tunneling machines around the world. From the US, from Sweden, from Switzerland, Japan, Germany, and the USSR were some of the first to operate in this manner. Some manufacturers built only one or two machines. Others, like Atlas Copco of Sweden and Muir of Germany, continued to work on improving their technology for a period of the next 40 to 50 years. And we'll run through these very, very quickly. Robbins Company in Germany in 1957, very unusual design. The USSR had built this tunneling machine in 1960, also gear-type rolling cutters. The Komatsu tunneling machine in 1963, Komatsu became a licensee of the Robbins Company, and they built a shielded hard rock tunneling machine which could expand and retract within the center of that hard rock shield. Ingersoll Rand and Lawrence in 1964 built this kind of machine with a pilot pull capability, and it actually gripped and pulled the entire machine forward for its cutting thrust. And this machine was built by Hughes Tool Company in 1965. It was called the Betty 1. It completed a very successful long water supply tunnel and was the first machine to use electronic lasers to steer the machine. The next is a joint project here from two countries, Habegger and Wohlmeier in 1966. Habegger of Switzerland and Dr. Wohlmeier of Austria conceived of this undercutting technique, which was very successful in very hard rock, but the cutters didn't last very long. And so this became a development which was acquired by Atlas Copco. And then Jarva in 1966 in the US. Jarva built a whole series of tunneling machines quite successfully, and they also were acquired by the Atlas Copco Company. So now to discuss some new directions which the Robbins Company took, starting a bit further back. In 1961 and 62, the Robbins Company was offered the opportunity to design and build a high-speed rail tunnel machine for Paris, for the Paris RER Metro. This was in a very mixed ground, rock and soil, well below the water table and running right near the Seine River. This required the new machine that would work with excluding the groundwater while the rock was being cut and evacuate the rock out of the tunnel. This was a case of a successful innovation. The first rotary cutter head pressure bulkhead shield. This machine used compressed air behind its rotary cutter head to control the water pressure and support the face while allowing men to operate in free air. It was 10.3 meters in diameter, and the machine withstood up to, withstood 2.5 atmospheres of pressure. Here you can see the cutter head of this machine being lowered at the étoile in the middle of Paris, and the kind of segments which were used, which were bolted and sealed. So So there were a lot of new features in this. So now another new development, double shield for bad rock. The design was originated by myself on a flight from France to Italy. The machine utilized two shields, interlocked and protected the machine and the tunnel from rock falls from the tunnel face to the point where the segments were installed. I had made a visit to Carlo Grandori in 1972. Carlo was using a 6.4 meter open rock boring machine installing precast concrete segments at the Brassamoni tunnel. That was also a new concept. And so I reviewed my sketches with Carlo Grandori, and his reaction was positive. The company was positioned to, this is the Saley company, his company, to be in the forefront of the double shield tunneling machine from then on. The next project is about the Channel Tunnel. A few years later, the Channel Tunnel was again on the top burner. This tunnel was a world significance because it had been under design and startup for over 100 years at this point. Here's one of two machines built by Colonel Beaumont, which bored 1.8 kilometers of tunnel at that time before work was stopped due to political pressure. But then we have the next near start for the third time, which was 1973 and 74, when two machines were built, one by Robert Priestley Limited and the other by the Robbins Company. Here you can see a single shield machine with an independent gripper ring following the shield, and then expanded precast segments behind the gripper ring. The project was canceled by the British government just as the Priestley machine was completed and delivered. However, a 30-meter long test tunnel was built to demonstrate that what the machine could do, and it did very well. They bored that 30 meters and could have just kept going. The Robbins machine at that time, is, in 1974, Priestley and Robbins were together. Robbins' machine used cast iron segments erected within a double shield. This machine was never put underground, but eventually was boring sewer tunnels in Turkey. Then in 1987, and this is a story that most of us already know, final approval for the Channel Tunnel, and this was the job that would actually get done. France and Great Britain signed the agreement by Francois Mitterrand and Margaret Thatcher, and here you can see there were 3 tunnels. They required 6 machines for the undersea portion of the tunnel and 4 other machines for the land-based approaches. And we'll go quickly through these. The British side service tunnel machine. This was built by Howden and Company from Glasgow. And it was a double shield machine. This was a design which was based on our patents, and we were induced to agree to a license arrangement here in order to remain qualified for supplying the other British machines. And we are very happy that we did that. The machine used on the French service tunnel, is here, was an articulated single shield with a telescoping cutter head. And this machine would work in very, very weak rock below the see up to 10 bars of pressure. This machine used the first large diameter double piston discharger to lock the tunnel muck out from this very high pressure into atmospheric pressure. And you can see here the light blue is the pressurized part of that machine, which was 5.6 meters in diameter, and the double piston discharger at the very back of the screw conveyor. The British side running tunnels, which were the main rail tunnels, are shown here, 8.3 on the British side, and on the French side, this was a telescoping cutter head design like we had designed for them. And this was a joint venture between Robbins and Kawasaki of Japan. Most of this equipment was built in Japan and in France, and they used a backfill grout very close to the cutter head so that there was less chance of failure. 2 service tunnel machines completed in 1991. There was a ceremony with a breakthrough at Dover Castle. This is a shot of 2 breakthroughs occurring again when the main rail tunnel is completed, as the French machines bored into the openings connected by the British machines. So here we have a little discussion about concepts that did not work. And actually there were quite a few. The first one I show here is a walking gripper machine built in 1962. This is stepping back now quite a ways. It was a 2.2 meter sewer tunnel in Virginia. The idea was to use these 8 longitudinal grippers just behind the cutter head. And this machine really did not work because we modified it very quickly into a regular gripper type design. This hydraulic system was way too complex for us to fix in the tunnel. The next shows a machine from the 1974 bored the Vat Tunnel in Utah, and it also had a walking gripper mechanism. Next here is a Westphalia Lunen walking gripper in the 1980s. This machine was for a project by Hochtief for a rail tunnel. It was added complication that the concrete lining was pumped in behind the shove jacks and used as a thrust reaction. At the same time, it pre-consolidated weak rock. It did work, but was never tried again. And so a few comments now about the culture of risk. Risk seems to grow for very heavy construction as the world economic system deteriorates. One possible solution is to use new models of contracts. New contracting models have been studied by the ITA and several other groups. Design, bid, build adds a lot of new responsibilities to the owners and to the contractors. The build, own, operate system was expanded financial partners. Bigger projects may increase risks and increase political risk for the public. Litigation risks increase and legal issues become more important. So standardization and simplification become very appealing. Here's a classical risk-sharing relationship. The tunnel owner or designer at the top, the contractor tunnel builder on the right side, and the equipment developer and manufacture on the other side. And this has to be balanced, and it has to be understood by all parties. And when we start making huge mega projects out of these jobs, the responsibilities of the three parties become quite complex. In seeking relief from these risks, experienced international tunneling contractors have begun to look to emerging markets. This is in the Southeast Asia area, the Middle East, and Eurasia. Contracting practices in these areas are growing and may provide a more welcoming environment to innovate designs and solutions and a less litigious atmosphere. We have some recent innovations here. The SR-99 tunnel in Seattle, Washington is a state route that is an economic challenge that is a trend for the limiting the risk. Examples can be found where innovation is encouraged. So in SR-99 in Seattle is a replacement for a waterfront elevated viaduct damaged by an earthquake. Here we can see this is a model of the world's largest tunneling machine, 17.48 meters in diameter. The prime contractor is Dragados of Spain, with Tudor Saliba and Perini as partners, and they selected Hitachi Zosen of Japan to design and manufacture the machine. Pressure compensated disc cutters are part of one of those innovations with 7 bars of potential pressure, and these are under assembly at this point. You can see the machine is not yet assembled fully at the job site in Seattle, and the new pressure compensated disc cutters are shown here. So more on the modern innovations. In my opinion, these should be brilliant, fast, and cheap. There are many opportunities to make improvements in tunneling machines. The concept of this concept was developed by a contractor from Ontario, Canada, and is to provide a continuous, flexible support system very close to the tunnel face. This method solves a need simply in a way that works. It can be implemented quickly and is relatively inexpensive. We've used this design for the Olmos project in Peru under the high Andes Mountains. And this job has very severe rock bursts, which the machine was able to go through, except for the worst possible ones, which just crushed the machine. So these support elements are longitudinal slats. There's a great deal of advantage in using longitudinal supports, and pockets are included under the roof canopies. And here's a design a drawing that shows how these slats are installed, overlapping, held together with rock bolts and very light segments of ring beams. Now, there is a little video here, and so there you can see this shows the bangs and the noise is small rock bursts. There you can see the supports are still holding this up, even though the machine is actually sort of coming apart. So let me continue a little bit to conclusions here. One of the current ITA initiatives is ITA Tech, and we've heard a little about that. This group is pushing new concepts forward in a manufacturing-centered group. They strive to achieve a consensus, and good work has already been achieved. The main bearing ratings and low rebound shot creep, among other things. So let me just make the last comment, if I may. In epilogue, there was those of us who spent much of our lives in underground construction find pride in innovative design. The way forward is the future of tunneling is through a collaboration between the ground, the tunnel openings, and the people who work there. This is our environment. We should pass on the excitement of creativity to young engineers, builders, and designers, both men and women, to follow our future underground. Thanks to all of you for the opportunity to speak to you.